You know, I really don't envy these digital fashion designers who create clothing for a blockbuster animated movie or a video game. Well, you have two terrible choices. One, you use low-quality, coarse geometry. Of course, this runs fast, but that piece of clothing will look like it is made of stiff cardboard. No good. Two, you use a high-resolution mesh with many millions of tiny triangles. Now this looks like what it should look like, but, of course, your computer catches fire and it takes 3 weeks to simulate 1 second of footage. So, quality or speed. Guess what will work for your scene and hope for the best. But what if we didn't have to guess? Okay, what? How? Well, take a really coarse input geometry like the one here and then give it to this technique and it creates an optimized mesh that puts detail exactly where it is needed and nowhere else. So, just to make sure, this runs super fast, this runs super slow, and between the two, there is the new technique that looks nearly as good as the slow technique, but it gives you this result quickly. Think of it like a smart budget manager. Instead of spending $1 million on every single part of the movie, it spends the big bucks only on the lead actor's close-up and saves money on the background extras. So this can give us incredibly high-quality results at the fraction of the cost of a full simulation. I mean, just look at that. The movement of this ridiculous puffy jacket is just mesmerizing. And now, check this out. Yup, this is the incredible underlying geometry behind it. I can't stop looking at it. Especially that this geometry has a little secret. What is the secret? Dear fellow scholars, this is 2-Minute Papers with Dr. Károly Zsolnai Fehér. Well, it uses a crazy equation that relates the stiffness of a material to the wavelength of its wrinkles. It's like a master tailor. It just looks at the material and knows in advance what kind of wrinkles are expected from it. It knows in advance how materials will stretch and fold. And then it creates these triangle meshes that are a bit elongated into one direction. Why? Well, because they align themselves with the direction of the wrinkles. That is absolutely incredible. This sounds like science fiction. Look, here is a more uniform mesh. Computing this will be expensive because it does not follow the material properties and the wrinkles. It wants to put detail everywhere, all the time. And here is the new technique. That looks... wow, I am out of words. Look at how beautifully it adds more geometry around wrinkles and much less at less interesting areas. It's a bit like paving a road. If the road is straight, you can use long slabs of concrete. No problem. However, when you know that it takes a big turn, you'll need a lot of smaller tiles to follow the curvature of the turn. But only then. And this is the secret sauce that makes the new technique so efficient. Genius! And here's the kicker. The new method works completely differently from the older ones because those are reactive. They work a bit like students work for a deadline. They run the simulation, see that a problematic wrinkle is starting to form and, of course, wait until it's too late, and then frantically try to do something in the last moment, hair on fire, and, of course, it doesn't work. Now, hold on to your papers, fellow scholars, and check this out. The new technique changes the geometry during the simulation based on how much the cloth is currently stretching or compressing. What? This is insanity! It knows what is going to happen even before the simulation takes place. Now, when reading the paper, I thought, okay, this will work for simple flags or capes. Great, but nope. They showed it working on complex, multi-layered garments with collisions. It handles the interaction between different layers of cloth so well, which is notoriously difficult. Now, this technique is still not perfect. I'll show you a weak point in a moment. Another subtle but important thing. The method is solver agnostic. they plug this adaptive mesh into standard cloth solvers without modifying the model or collision pipeline. This means it can be layered on top of existing production systems rather than replacing them. That is huge! For studios, that is the difference between a research demo and something you can actually ship. Loving it! This work is from Huamin Wang's group. He is a legend in physics-based animation, consistently finding ways to make virtual worlds more realistic and faster at the same time. If you see his name, you know it's gonna be good. Now, good? Yes, but not perfect, since it relies on predicting wrinkles based on static properties. If the cloth gets tangled in a chaotic, unpredictable knot, its calculations might not be good enough to capture this chaos. It's like a weather forecast, perfect for most days, but it might miss a sudden, freaky thunderstorm. In an era where almost every paper we see is AI this and neural network that, this paper is purely physics-inspired. It solves the problem analytically, using fundamental mechanics and not by training a black box on a million images. Just physics and human ingenuity. I absolutely love that. What a time to be alive! And, frankly, nobody talks about this enough. This is human brilliance at its best that makes next-generation games, movies, and all kinds of simulations run on our home computers. Now, once again, almost nobody is talking about these papers. People just don't know that all these amazing works exist. So, help us save a paper today, subscribe, hit the bell, and leave a really kind comment. So, no more blocky capes, just beautiful drapes in all kinds of shapes. Subscribe to 2-minute papers. That didn't rhyme at all. Here you see me running the full DeepSeek AI model through Lambda GPU Cloud. 671 billion parameters, running super fast and super reliably. This is insane. I love it, and I use it on a regular basis. Lambda provides you with powerful NVIDIA GPUs to run your own chatbots and experiments. Seriously, try it out now at lambda.ai/papers or click the link in the description.